For a very long time, humans have imagined what life may be like in other worlds, thanks to the James Webb Space Telescope, JWST, the most powerful telescope in existence. That question can finally be explored while observing the closest star system to us, Proxima Centauri, which is only 4 light-years away. Scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima B. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore the JWST's terrifying discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence, SETI project in 1984. The nonprofit's objective is to gather spaceborne radio signals, as radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. However, in the past 30 years, no verifiable alien signal has been discovered. Following that, the JWST's successful launch has aided in the quest to examine a range of undiscovered planets orbiting distant stars. As the largest telescope in the world, floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, it has the potential to uncover significant findings. 20 years ago, there were no known planets outside our solar system, but since then, more than 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft, on its route to Jupiter, turned its equipment back toward Earth and found a definite indication of the presence of plants, detecting the vegetation red edge, VRE, biosignature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth covered in a jungle should have a strong and easily detectable VRE signal. The JWST will measure the VRE of far-off, Earth-like planets in the habitable zone around stars, which could provide important signs of life in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST may be able to detect it as it enters its atmosphere. The missing wavelengths would then be discovered via spectroscopy, as atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres similar to our own, characterized by a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. For example, chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products, would likely be noticeable to aliens monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. However, life on exoplanets might not resemble life on Earth at all. Sometimes even earthly life forms like extremophiles, species that can endure in environments where other living things would perish, can seem alien. This group of organisms, primarily bacteria, can withstand extreme conditions such as heat up to 250 degrees Fahrenheit or strong acid with a pH level below 3. Since planets like Earth are more likely to support life than those with severe temperatures or acidic conditions, it could be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is classified as a yellow G-type star. These stars are less common and typically have shorter lifespans. However, in our universe, the likelihood of studying planets orbiting red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. This extended time frame allows for the formation of life and evolution to produce complex life forms. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, might have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star radiates light that is similar to that of Earth. Due to the close orbit of its planets, the best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is about 600 times fainter than the Sun, so a planet must be 20 times closer to it than Earth is to the Sun in order to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, a Goldilocks-like habitable zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, lifeless planet, given that it orbits its red dwarf star at a distance of only 4.6 million miles. This close orbit exposes it to strong solar winds that can completely destroy its atmosphere. However, Proxima B does receive enough sunlight for temperatures and liquid water similar to those on Earth. Due to its close proximity to the star, Proxima B is thought to be tidally locked, always showing the same side to the star, much like the Moon does in relation to Earth. Proxima Centauri is about 18% the mass of the Sun and burns far less brightly than one might expect for a planet so near to its star, just 5% of the Earth-Sun distance. It may appear to be a red-hot cinder. Liquid water could exist on Proxima B as long as the planet has an atmosphere to hold heat, since the total energy reaching it from the Sun is only 65% of what Earth receives. However, the planet is not especially friendly to life. It is most likely tidally locked, meaning it always faces the same direction toward the star, producing permanent day and night sides with significant temperature changes. The planet also receives 100 times as much high-energy radiation as Earth does, including X-rays and ultraviolet light. Due to its proximity to Proxima Centauri, Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a shielding magnetic field similar to Earth's, the conditions for life may not be favorable. Certain realistic conditions could potentially make Proxima B a more pleasant world. Sadly, models suggest that the atmosphere of tidally locked planets may be susceptible to rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we don't know anything about Proxima B's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. However, since an atmosphere presupposes the existence of CFCs, and the two taken together presuppose the existence of life, we are desperate to know if Proxima B has a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine if it crosses its star's face as seen from Earth. These transits would let scientists determine the planet's size and mass, which would enable them to assess its density and validate the planet's rocky makeup, providing information on the materials used to create those rocks. During a transit, starlight might disclose the nature of the planet by passing through its atmosphere. However, the likelihood that the orbit will be in the right alignment for scientists to see a transit is merely 1.5%. The star's propensity to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is tricky, as stellar heat causes a rocky planet to absorb sunlight and emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. Additionally, the JWST was created specifically to study infrared light. Proxima B's infrared heat signature is the key to identifying the planet's atmosphere. Moreover, the infrared portion of the spectrum has a strong affinity for the JWST, which may allow it to observe city lights on Proxima's night side, even if they are as faint as those currently employed on Earth. The JWST could detect artificial illumination as long as it is constrained to a frequency band that is 1,000 times narrower than the star's light. Proxima B's day side may be heavily coated with solar panels reflecting starlight, as Proxima B revolves around its star. Day and night are identical, with cool evening lows following daytime highs. The difference in temperature between day and night, however, depends on whether or not the planet is entirely composed of bare rock. An atmosphere and ocean both conduct heat. In other words, if there isn't an atmosphere, Proxima B's dayside and nightside temperatures will differ more. In fact, since the dayside will emit all of the energy it receives from Proxima Centauri as a black body, we can calculate the precise amount of black body radiation that should be present. The night side, on the other hand, would look like a frozen form of hell. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will only take the JWST 11.2 Earth days to measure the infrared radiation from Proxima B's two faces after it has successfully completed its orbit around the star. In the event that Proxima B has an atmosphere, the next step will be to analyze its makeup. The presence of gases like oxygen, water vapor, and methane in particular could indicate the existence of habitable circumstances, if not actual living things. However, to accomplish this, we must successfully capture starlight as it bounces off or travels through the planet's atmosphere, which is a very difficult task. The JWST can only closely examine a few of the closest potentially habitable worlds because it was not built to look specifically for extraterrestrial life. Additionally, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. The JWST is unable to detect the presence of unbonded oxygen, which is the strongest sign of life. Even if some mixtures of these gases may suggest life, one of the planned ground-based observatories that will be able to conduct a thorough atmospheric investigation is the extremely large telescope, scheduled to begin operations in the middle of the 2020s. Ozone may be among the substances that the JWST is capable of detecting. Until those telescopes are operational, the JWST may provide information that we can consider for a decade into the future. Even more powerful space telescopes may employ cutting-edge techniques to conceal the blinding brilliance of a planet's host star and reveal starlight reflected back from the planet, somewhat akin to covering the lights with your hand to improve your ability to see distant objects. Future space telescopes might achieve this by using small internal masks or large outside umbrella-shaped satellites. After starlight is blocked, studying light reflecting off a planet becomes much easier. Unfortunately, the majority of gases produced by terrestrial life can also be produced by non-biological factors. For example, methane is a gas released by both cows and volcanoes, and sunlight can convert water molecules into oxygen and hydrogen through photosynthesis. When searching for alien life, astronomers are sure to encounter some false positives. Therefore, astronomers must have a thorough understanding of a planet of interest to assess if its geologic or atmospheric processes potentially resemble a biosignature and help rule out false positives. The next wave of planet research may produce the compelling evidence required to establish the reality of life. The JWST's preliminary data gives us a preview of the significant advancements to come. If there is life elsewhere in the cosmos, it represents one of science's most pressing questions. It is possible that life is abundant throughout the cosmos, or it may be that we are completely alone, trapped on a solitary planet in deep space. In either scenario, significant philosophical or psychological adjustments among people will likely be necessary for the eventual resolution. The search for extraterrestrial life has captivated humanity for centuries, inspiring countless stories and theories. As we advance technologically, our understanding of the cosmos expands, revealing new possibilities for life beyond Earth. The use of space telescopes like the JWST not only enhances our ability to detect distant planets, but also allows for detailed analysis of their atmospheres, helping scientists identify potential biosignatures. Moreover, the exploration of exoplanets fuels collaboration across global scientific communities. International partnerships in space research foster knowledge sharing and resource pooling, increasing the chances of significant discoveries. These collaborative efforts also enhance public interest and engagement in space exploration, as findings are often shared with a broad audience, igniting curiosity and imagination. Additionally, the philosophical implications of finding life elsewhere prompt deep reflections on our existence. Would the discovery of alien civilizations change our understanding of life's purpose? Such questions challenge us to rethink our role in the universe and our relationship with our home planet. As we continue to refine our technologies and methods for exploring the stars, each new discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving the quest for knowledge and understanding beyond our earthly confines.